Okay, hello everyone. Welcome to VSPG. Today we're hearing from Professor Ben Johnson from Iowa State, talking about oxygen isotopes and hydrothermally altered ocean crust records seawater δ18 evolving with continental growth and emergence. Let me introduce Ben and we will get going. So, Dr. Ben Johnson is a geologist and geochemist with broad interests that span Earth history and Earth system science. He uses a variety of rock archives, including chemical sediment, glacial tills, and igneous rocks as records of the interactions between life, the oceans, the atmosphere, and the solid Earth over deep time. He uses fieldwork, analytical and isotope geochemistry, and numerical modeling to investigate deep time questions about Earth history. He's also interested in astrobiology and planetary sciences. So thanks a whole lot, Ben. Ben stepped in just very last minute to fill a space we had. So he's our hero this week. So that's great, and we're really excited to hear about this project, Ben. So please go ahead.
Awesome, great. Yeah, thanks, Alex, and thanks, Andre, for the invitation. Yeah, just coming back from being on paternity leave for a little bit, so still getting back into the swing of things. But this is a nice way to kind of get welcome back into science and to research work. So before I jump into the sort of the subject of today, I just wanted to sort of highlight some of the work that my group is doing here at Iowa State University in the Earth System Evolution Lab, or EASL. For a nice acronym. There's a handful of us right now, a former graduate student, Dana Meinert, whose a lot of her work I'll be showing today. There's currently 3 PhD students in the group, Sam, Alex, and John, all working on sort of various aspects of the connections between sort of the different spheres of the planet over deep time. And so we've got some kind of different research areas going on at the moment where we're trying to apply Earth system science to planetary evolution. We have some deep time sort of nutrient cycling with whole Earth nitrogen and focus on some nitrogen geochemistry during the Neoproterozoic snowball Earth. That's sort of Sam and John's work. Alex is really pushing forward some cool analyses of fossil plants and their nitrogen and carbon isotope composition as records of kind of surface Earth system changes through time. And the third area that we work on, which is what I'll be talking about today, and a lot of which was from Dana's master's thesis, is continental emergence and uplift. And I'll have a short teaser at the end about some other future directions applying to paleoaltimetry in this area. So just a little bit about us before we get into the talk. And at some point I was preparing a version of this talk and I was reading this great book by Lauren Groff called Edible Delicate Birds. And there's this quote in there that I thought sort of fit with the kind of the theme of this talk. So I'll just read it out loud to try to set the stage for the material today. So there's no ending, no neatness in this story. I think this is a book of short stories, and this one I think was about a woman who was married to like a sea captain, and he was out at sea and she's waiting for him to come back. So there never really is where water is concerned. It is wild, febrile, kind, ambiguous. It is dark and carries mud, and it is clear and the cleanest thing. Too much of it kills us, and not enough kills us, and it is what makes us, mostly. Water is the cleverest substance, widely beyond the stretch of our mortal imaginations, and no matter where it is pent, no matter if it is air or liquid or solid, it will someday, inevitably, find its way out. And so we're going to be using the way water moves and how water and rock interact in this talk to learn some things about continental crust and the emergence of those continents in deep time over Earth history. And that's sort of a big motivation for this work. Earth is unique in many ways among our planetary neighbors. It's the only planet with life. It's the only planet we know of with plate tectonics. But another feature of our planet that's unique is we have a bimodal crust, right? We have relatively buoyant, thick continental crust that sits higher, at least it does today, than denser oceanic crust. And so we have this unique topography compared to, say, Venus on the left there and Mars on our right. Despite this feature of our planet that's fairly unique, there's not a really, and specifically what I am interested in here is, well, both the generation of continental crust, the material continental crust, but also when that crust becomes emergent above sea level. So when that crust can interact more directly with the atmosphere. And emergent continents act on planetary sort of scales. They affect climate and life through weathering, albedo, habitat, spaces, nutrient delivery. And we've known this for a long time, right? Here's a depiction of the carbonate silicate weathering feedback from casting 95, where the interaction of the atmosphere with emergent land surface has a major influence over many features of the Earth system, climate, albedo, all these sorts of influences. But despite its importance, right. And so I like to think of this too as sort of the distinction between two movies now. I know that Dune is out. I've seen the first one and I haven't seen the second one yet, but we're sort of in the middle here on Earth, right? Between a Kevin Costner Waterworld situation and Frank Herbert Dune 1 and/or 2 situation. And my fun fact about myself is I went to a birthday party when I was 12 to see Kevin Costner in Waterworld in the theaters, and then we went to a swimming pool and had a pool party afterwards. So you can figure out how old I am if you want, based on that. But this is kind of the framework we're working with, right? Emergent crust is a big factor, right? And it can be the difference between sort of Kevin Costner world and a Dune type planet here. However, we don't really have a great understanding, or there at least are a number of estimates that vary widely on when significant crustal area emerged above sea level. And so I'm showing here a time scale from 4.5 billion years ago to today, just with some published estimates of when continental crust first became emerged above sea level. So there's work, by Roger Buick and Don Lowe looking at outcrops sort of scale things, angular unconformities, the presence of conglomerates, braided streams, extensive passive margin deposits by 2.5 billion years ago. And there are even some thermal models by Sinti Lee and others that suggest that the evolution of Earth's mantle structure and temperature wouldn't have allowed for significant crust until the Neoproterozoic, perhaps. And so there's this wide range in dates of emergent crust, and specifically we are interested as well in significant areas of emergent crust. This is what I mean by, having a planetary scale sort of impact. And so if these geologic and some modeling, angles are not sort of aligning to the same kind of time scale, we want to look for other tools that we can use to try to narrow down this estimate age range. And so what I'll propose here is that we can use the oxygen isotope history of seawater as a proxy for continental emergence. And so we're going to be talking a lot about oxygen 18, δ18. So I've defined that down below, where we're comparing the ratio of oxygen 18 to 16 in a sample to that of a standard. We standard mean ocean water here. And so in order to justify us being able to use this value through time as a proxy for continental emergence, it's worth asking and then trying to answer what actually controls this value, δ18 value of seawater, over Earth history. And so it all sort of comes back to something that, at least I learned in maybe elementary school, and we're thinking about the water cycle. And so what I put up here is just a schematic of, the oceans, continents, and this is what we learn about as the water cycle when we're sort of growing up, right? We have evaporation of water off the ocean, forms clouds, rains, snows over land, rivers and groundwater come back to the ocean, and there's our water cycle right there. But of course, as geoscientists and earth scientists, we know there are a number of other important fluxes in this system. There's the interaction of water and rock in a number of different settings, including weathering on the continents, hydrothermal alteration of the oceanic lithosphere, as well as deep earth water cycling through subduction, entrance into the mantle and outgassing at mid-ocean ridges or other places where volcanoes are active. And so really this deep time water cycle is mediated by water rock reactions. And there are a couple of those that are sort of extra important. And these combined these are what influence, and these are what set the δ18 value, the oxygen isotope value of seawater, over multi-million to billion-year timescales. And there's sort of a couple key reactions here. One of them is weathering on the continents. Weathering on the continents is a relatively low temperature process. And so this tends to take oxygen 18 out of meteoric water, rivers, groundwater, and sequester it in alteration minerals in the crust. So the continents are a sink for oxygen-18. The other major interaction here is hydrothermal circulation of seawater through the oceanic crust. And this has sort of two effects on the isotope value of seawater. Alteration of crust at shallow levels, and I'll show a more detailed picture of this in a couple slides, tend to do the same thing as continental weathering, where we're taking oxygen-18 out of the fluid, sequestering it in the rock. At higher temperatures, deeper in the oceanic crust, that's what's shown in this red value here, the relationship is flipped actually, where oxygen-16 tends to go from the water to the rock. So the fluid will have a higher delta-18 value compared to what it started after interacting at these high temperatures. And so today on Earth, the combination of these two fluxes, these two water-rock reactions, buffer the oceans if they're ice-free to a value of about -1 per mil. And the key thing I want to point out here is that emergent continental crust will change this buffering value of seawater. If crust is above sea level, then low temperature weathering can happen, and you can have that sink for oxygen-18 in the continental crust. If the crust is below sea level and it's not interacting and not weathering in that way, then it won't act as that sink, and the ocean should respond, therefore, by having a higher delta-18 value, because you're missing that one sink for oxygen-18 in this sort of geologic water cycle framework. And so what we're going to actually ask here is, there have been lots and lots of attempts to use the chemical sedimentary record. I have a schematic carbonate platform over here on the left-hand side of the diagram as a proxy for this seawater delta-18 value through time. And I'll come back to these a little bit at the end. But there's some challenges with using the sedimentary record. Carbonates can be reset, they can be diagenetically altered. And so I'm not saying in this talk that those values, don't mean anything, because there's clearly meaning in those data, and we'll see that later. But what we're going to ask instead is, can we use this other place where water and rock interact in a way that we understand to get after the delta-18 value of seawater? And so we're going to use our understanding of hydrothermal circulation through oceanic crust and lithosphere as a way to perhaps record the seawater's original delta-18 value before that interaction. And so just to zoom in a little more schematically on what that looks like, I have here a cross-section going from the ocean, at the top of this figure down towards the mantle. And we have seawater that's infiltrating, at 0 per mil. This is sort of a today seawater scenario. At cool temperatures and shallow levels in the crust, the interactions between water and rock tend to sequester, take oxygen-18 out of the fluid and put it in the rock. And as I said before, as that temperature heats up, you descend through the crust, the geothermal gradient increases the temperature of the water. That relationship is flipped, and it's the opposite. So now the rock has a lower delta-18 value, it takes oxygen-16 preferentially out of the water. This water, as it descends, once it heats up to a temperature of about 350 to 400 degrees C, reaches its maximum buoyancy, and it will be driven to return quickly towards the surface. It comes out at hydrothermal vents and, these sort of places, these settings at mid-ocean ridges today. So we think that this should be a relatively constant thing through Earth history. This is a thermodynamic control on the temperature that seawater gets to before it wants to return back up to the surface. So these processes, this hydrothermal alteration of oceanic crust, should operate essentially the same way over much of Earth history. There's some details in there about to what depth, perhaps, that temperature is reached, and that could be important. But this general process should be sort of conservative over Earth history. So we can use this understanding schematically to investigate these hydrothermal cells. Just comparing our schematic picture on the left of your screen, which I just showed, to some actual data. These are measurements from the Samail ophiolite in Oman, made by Gregory in 1991. And what we're showing here, structural height is just the depth in the crust, where the top there, 7 kilometers or so, that's the paleo seafloor, and we're descending through the crust with whole rock delta-18 values measured here with the points. And I've color-coded them just to be consistent with the schematic picture. So we know these rocks start at about 5.5 per mil. When you extract, partial melt from the mantle, The mantle is pretty consistently about 5.5 per mil in its oxygen isotope values through time, and so the basalts will match that same value. So we start at 5.5 per mil, and indeed the upper part of the crust has a higher δ18 value due to that low temperature interaction with hydrothermal fluids. And as you move deeper into the crust, the opposite relationship is indeed observed. So there's a really solid understanding of how this hydrothermal alteration affects oxygen isotopes in these settings of oceanic crust and oceanic lithosphere where water and rock are interacting. And so the question is then, great, we sort of observe these, we have a conceptual understanding, we make these observations in one-dimensional cross-sections, that's what I'm showing here. How can we expand on this and sort of quantitatively use the alteration patterns we see in these settings of crust to some way back out the initial value of the seawater? Because that's really what we're after. Does that crust sort of remember the oxygen isotope value of the seawater when it was first infiltrating into that setting? And so to do that, we're using an inverse method, and I'm going to walk through the setup here. And as a sort of motivating image to keep in your brain. I know it's morning for me. I've already had one coffee, but I could always use more. So I'd like you to think about espresso, and specifically espresso made in a mocha pot. I don't know if anybody uses these, but this is what I use every morning to make a coffee. And it's a really pretty great analogy actually for what we're doing here. So here we have, hot water that's heated down at the bottom of this coffee pot. It goes up through a solid material, the coffee grounds in this case, and it comes out as a different composition, in this case, coffee, out the top after this relatively high temperature interaction with something solid. So basically what we're doing here is we're going back to the coffee grounds after you've made coffee out of them and trying to figure out what the water was like before it turned into coffee. So we're using this. This is something I like to think about when I'm describing this. So if I don't think this will be too much, but you can anchor yourself in coffee, which hopefully is familiar to a lot of us. And so the approach here for this inverse method is, let's take a box of rock here. We have a box A, B, C, D. It has some initial δ18 value, delta Ri. If we say a fluid, say Q1, goes in across that boundary, AB, there's going to be some exchange of isotopes as a function of the temperature that exists at that boundary, right? So there'll be some fractionation and that value will change to this sort of delta AB value. Say that fluid flows through the box, comes all the way out the bottom, and it goes out across this boundary CD. Again, it's going to exchange oxygen isotopes across that boundary as well. And the rock, therefore, is altered from its initial value, delta Ri, to some final value, delta Rf. And so we can define this change in δ18 values for this box, delta AB, CD. And I have written this equation down here, and we're assuming a couple of things for this inverse approach. We're assuming both fluid and total oxygen mass balance for each of these boxes. So the fluid that goes in equals the amount of fluid goes out, and the total amount of oxygen in this box of rock stays the same. We're just exchanging isotopes between the fluid and the rock. And so, of course, in the real world, right, it's not just a one-dimensional problem. So we can add a couple other fluxes into and out of this box, vectors Q3 and Q4, to create this mass balance approach for a 2D reconstruction or a 2D inversion of patterns of natural data, which I'll show in a second. And so we can then create a number of these boxes to try to capture the natural variability in hydrothermal systems. So we can just add more boxes and add more mass balance equations here. You'll see that some of the boxes, they're going to share fluid flow vectors. They're flowing out of one box and into another. And so this is our sort of setup where we're just adding a number of boxes onto irregularly spaced sample data to create a regularly spaced grid with these mass balance equations shown here, defining the change in oxygen isotopes across these different boxes as a function of temperature. And so the full setup for this inverse method is we make sort of a bunch of boxes, a bunch of mass balance equations, and represent these as a matrix equation shown here on the right, where the oxygen isotope fractionation is this larger matrix, the delta AB, delta AD, etc., for each of the boxes. The fluid flows, so this is the total amount of fluid that's represented by each of these vectors. Here in this sort of longer vector has to equal the change in oxygen isotope values of that body of rock from its starting point to where it finished. And so we can use these things and we can apply standard inversion techniques to solve for this Q vector here. So what we're doing is we're using patterns and measurements of whole rock oxygen isotopes, some independent constraint on the temperature of alteration to invert and get the total amount of fluid that had to have flowed through this body of rock in order to produce these patterns at these given temperatures. Once we know that, we can use this second equation, which I'm trying to highlight here, where we can calculate the initial fluid or water δ18 values as a function of that water-rock ratio. So we invert for this W term. We know the amount of rock because of the way we set up our grid, our 2D grid. We measure the final rock's δ18 value. That's, you go sample it and you measure it. And then we constrain the initial rock δ18 value based either on an unaltered sample, from a nearby location, or by geologic setting. I think we can do that fairly confidently. And the big delta in this term is actually the average temperature of that water-rock interaction, which we can constrain or measure directly. So we're inverting this data to basically get the total amount of fluid that went through these systems, which we can then link to this equation from Gregory and Taylor in 1981 to estimate the oxygen isotope composition of the initial fluid before it flowed through these bodies of rock. And I'll show some data from natural samples as well, which will help sort of clarify the approach here. And so one thing that we're doing here is we're sort of building on really decades of work understanding the hydrothermal alteration and its effects on oxygen isotopes in the crust, in oceanic crust. And we're using this, I say quantitatively, and really it's a 2D reconstruction here. I think we're extending from those 1D profiles that I showed of the samalophyllite to a 2D sort of cross-section. And in this way, maybe we're getting an additional unique archive of ocean conditions. There's lots of places where water and rock have interacted in this way, and so there should be lots of sites where we can potentially apply this technique. And in detail as well, what we do is when I run this inversion, we take out one random sample each time. This is what we're calling a leave one out approach. And so we can run this inversion basically the same number of times there are samples in a certain location as a way to try and constrain some uncertainty in these settings. So we're getting an estimate of seawater δ18 with an associated uncertainty, as you'll see here. So this is not a completely new idea, but what we're doing here is we're expanding to 2 dimensions and using this sort of tracer mass balance inversion approach, which is commonly done in oceanic sciences and atmospheric sciences, but we're applying it here in the sort of hydrothermal world. So that's the setup. And when we were, developing this, we thought, well, it'd probably be a good idea to test it in settings and sites where we know what the answer should be, right? And so we applied the inversion to a few sections of Phanerozoic, altered oceanic crust, a section from the East Pacific Rise, a back arc basin set of drill cores from the Furoku area in the Sea of Japan, and the Solia Graben, which is Cretaceous ophiolite on Cyprus. And so I'm showing here the results of those inversions shown in the orange dots with associated error bars compared to the estimates of what seawater δ18 was during these times based on benthic foraminifera, so the bottom dwelling plankton during this time. And so what I'd like to point out, right, is we're getting pretty great alignment, which is awesome, between our inversion approach and the benthic foram record. And you'll notice the Y scale here too. This is just between 0 and -1 per mil. So we're potentially sensitive to, maybe per mil, maybe sub per mil if things are really good, kinds of changes in seawater δ18. And I want to point out too, I didn't mention this, that this approach integrates the sort of full hydrothermal history of a section of rock. So we're getting the average δ18 value over the lifetime of that hydrothermal system, which can last many hundreds to millions of years. So these are really sort of long time scale and relatively large spatial scale proxies for trying to get after seawater δ18. So the model seems to work okay, right, in places where we know what the answer should be. And so that makes us confident that we can extend this approach to deep time. So here's that same map with the Phanerozoic sites, and I've added now the sections we've studied in the Archean and the Proterozoic. So I'll show data from Panorama, which is a VMS deposit in Australia here, and then a couple of a late Archean and a couple Proterozoic sites in North America, Noranda, Snow Lake, and Pecos Greenstone Belt here. And just to highlight what some of these field areas look like, the Panorama District in the Pilbara in Western Australia is a really fantastic place. It's I'll show a simplified geologic map of it in a minute, but the outcrops there of these igneous rocks are as we know, right, complete and pretty amazing. And so you can really see the whole hydrothermal system at Panorama. So here we are standing on a granite. This is the Strelly granite, which I'll show in a second, kind of provided the heat for hydrothermal circulation at this location. And if you walk basically 8 kilometers away, or drive in the truck 8 kilometers away, here I am standing underneath a pile of pillow basalts that looked like they could have been erupted yesterday. So this setting is really incredible because it's been tilted and eroded in such a way that you can walk through an entire cross section of this oceanic crust at this point that captures the whole hydrothermal system. And these rocks are 3.24 billion years old. And I don't know, it's just fun to show, right? Like, where do you sleep and where do you camp out there? I thought it was really fun because in this place we camped in these big dry riverbeds, which only run during hurricane season. And so a really fun place to go. And I know, a bunch of us have been to this area, and we know the quality of public transportation is second to none out there in the Pilbara. So just to highlight this place, because it really is rather spectacular. So this is a volcanogenic massive sulfide district, and it preserves essentially 5 distinct hydrothermal cells. So what I'm showing here is a really simplified geologic map. This pink area is the Strelly granite, and that gray section there is a volcanic pile of basalts to basaltic andesites primarily. And this whole system, the volcanic pile was erupted and emplaced, and basically immediately after was sort of heated by the intrusion of this Strelly granite, drove hydrothermal circulation. At some point later, this whole package of rock was tilted. It dips to about 50 degrees off to the east there, folded slightly and eroded off the top. And so you do really get a full cross section through the oceanic crust from these hydrothermal VMS sites where this fluid was flowing out onto the seafloor, shown here in these big diamonds. Down through the whole section of crust to the granite, which was sort of providing the heat for this area. And this place is pretty remarkable in lots of ways. The mineralogy still reflects the hydrothermal circulation patterns, and so do the oxygen isotopes. This is a zoomed in cross section here. So we have structural depth. Again, the higher values are close to the paleo seafloor, down to depth and horizontal distance of one of these sections, the Kangaroo Caves VMS prospect. And what I'm showing here in the X's are sample sites. These are whole rock oxygen isotope values from Carl Brauhart. He did his PhD there, basically doing a ton of geochemistry, including oxygen isotopes in this area. And I'm contouring them with these colors to show their oxygen isotope composition, ranging from something like 3 per mil up to maybe 14 or 15 per mil, similar to what we observed in Samael. These are similar values, right, that we're observing. And so to perform our inversion, we take this irregularly spaced data set, these irregularly spaced samples, and extrapolate, contour them out to fill out a regularly spaced grid. So here's again the samples in X's with those grid boxes. These are our, say, mocha pots, right? Our coffee pucks here, defined by the stars there at the corner of those grid boxes. So we regrid and we perform these inversions across these big areas. I'm just showing this one hydrothermal cell here, but these inversions are done over the entire area of this hydrothermal circulation, sort of as one big unit. So that's sort of the approach that we're using here. Like I said, we've also now extended this into the late Archean and Proterozoic. We use some existing literature data for Noranda and Sturgeon Lake, as well as Snow Lake in Ontario and Canada, and some new data that Dana, who's pictured here with me in the field, from the Pecos Greenstone Belt in New Mexico. This was fun field work to do, partly because it's about 30 minutes from where I grew up, so I got to feel like a big grown-up and bring my grad student back to hang out with my mom for breakfast, which is kind of funny. Awesome. So, we have all these sites where we've got whole rock oxygen isotope measurements. We have independent temperature constraints, either from fluid inclusions. We did chlorite geothermometry for Pecos. And so we perform these inversions. And before I show you the data, I think it's useful to place our constraints with similar work that's been done trying to estimate the δ18 value of seawater using other altered crust records. So I'll fill out this figure as we go here, showing a time scale from 4.5 billion years ago to today, with estimated seawater δ18 value here on the right-hand side of this diagram in per mil. And so here's some results from previous work. The one that's at 4.5 billion years ago, this is actually my calculated estimate of what a magma, what the oceans would be, or a steam atmosphere if they were in equilibrium with the magma ocean. You know, the mantle is 5.5 per mil, so the ocean should have started a little bit higher than that as it degassed from the mantle. This bar here at about 3.7 billion years ago, these are estimates from Emily Pope et al., I think 2012, from Ishua, from serpentinites in Greenland. And the other ones down here in the Neoproterozoic to Phanerozoic are a number of 1D ophiolite sections. I should add, actually, there's another one by Holmden and Muhlenbach that is about 1.7 billion years old that shows up sort of between -2 and 2 per mil over here. So we've got these previous records showing here, and our estimates of Phanerozoic values fit within this little orange box here that's close to modern day. It sort of shows some more detail in there, but it's well within that estimated range. And so here are the results from our inversion in these black dots here. Couple things you notice is we're filling in, this area in the middle between the sort of the early Archean and the Mesoproterozoic. Again, I'll highlight that there's an additional estimate from an ophiolite by Holmden and Muhlenbach that's about, I think it's 1.8 billion years old, but it brackets, our values really well here. So we have some data here, right? We have some constraints, we have some error bars. The error bars are relatively small here. That's partly a function of the number of samples from each location. Places with lots of samples have their error bars driven down because of our leave one out approach. But we're starting to see some structure, right, in here in these other compared to these other altered ocean crust records. And so, first order observations from this data, right? Our results indicate seawater δ18 was relatively high. Today, if it's an ice-free world, it's -1 per mil. And so we're, maybe 4 per mil higher than that, which is a significant change in the δ18 value of seawater. And it decreased at some point, during the late Archean into the Mesoproterozoic. And I'll talk a little bit more about some potential mechanisms for that change, here in a few slides. But we can make these sort of first order observations from this data. I'll point out as well that some recent triple oxygen isotope work in some chemical sediments also are consistent with a relatively high or enriched δ18 value for Archean seawater. So there are measurements from the fig tree barite from South Africa, and they did some sort of Monte Carlo simulations to try to estimate the control of that d'A18 value, and they use triple oxygen isotopes as well there to determine the balance of sulfate production, between microbial, what the microbial component of that was versus abiotic, and their results are consistent with a relatively high, plus, I think their range was 0 to 5 per mil, δ18 value of seawater. This is from Olsen et al. in 2023. There are also some relatively new measurements of triple oxygen isotopes in cherts, where these also support or are consistent with their formation from a relatively high δ18 value of Archean seawater. Either primary seawater, or the authors suggest this could be, hydrothermal fluids that perhaps interacted with the oceanic crust and are elevated in that way. But these data, if they're plotted on sort of a cross plot between oxygen 17 and oxygen 18, are consistent with being formed from a fluid with a relatively high δ18 value of seawater, or a fluid with a relatively high δ18 value, which could be, Archean seawater. So, we're not totally out to lunch here with our altered ocean crust or our hydrothermal setting estimates. We are both consistent with some previous work on, hydrothermally altered lithologies, as well as some newer measurements from the triple oxygen isotope community. Awesome. So, we make these observations, right? And it's a natural next step, and it's much more satisfying if we can try to put forward a mechanism to explain this observed trend in the δ18 values of seawater that we're seeing that were high and have dropped to their modern value sometime between the Archean, the late Archean to sort of Mesoproterozoic. And so what I'm going to show now is a series of model runs. So these are this is an oxygen isotope model based on Muhlenbach's 1998, where he compiled the total amount of fluid that sort of goes through all of these geologic water cycle steps and the fractionation, oxygen isotope fractionation associated with that to calculate a sort of steady state seawater δ18 value as a function primarily, again, of hydrothermal circulation and weathering on the continents. So those are the two biggest levers that control or buffer the δ18 value of seawater over these multi-million to billion-year timescales. So just as an illustration, let's set this model up just as it works today. Let it run. Let's see what happens here. And so that's what I'm showing here. So this is presuming all the modern fluxes of weathering, hydrothermal alteration, operating as they will, subduction, just everything as it is today. And here's the result. If we start from this relatively high value of 6 to 7 plus 6 to plus 7 per mil, this drops really quickly. And this is primarily a function of the great volume of water that participates in hydrothermal alteration of oceanic crust. So over the course of tens to 100 million years, we quickly drop down to modern seawater values. No surprise, we just said the model, do what happens today, and it gives us what happens today, right? But you'll notice it matches none of the data from the Precambrian. So then let's see what happens if we just simply turn off all of the continental fluxes. So we turn off weathering, we turn off the subduction recycling of water, we turn off all of the fluxes in this model that are associated with emergent crust, or continental crust. What would happen? Well, we can predict a couple of things. And here's the result of that. So this dashed line in the middle shows the result of these runs where we initialize the model, we turn it on with everything except the continental fluxes. So no weathering happens. Well, you still drop down, right, at the same time scale, because again, hydrothermal circulation through oceanic crust helps buffer this value relatively quickly over this sort of time scale. But instead, you're at a steady state value that's much higher than modern, right? Maybe plus 3, plus 3.5 per mil. This is because, again, weathering on the continents is a relatively low temperature process. It's a sink for oxygen 18. So if you don't have that sink for oxygen 18, the ocean has to respond by having a higher δ18 value. And so here's a model run where we turn on, full continental emergence occurring between, say 3.2 to about 2.5 billion years ago. Well, you notice that matches our, late Archean to maybe early Proterozoic data fairly well, but it misses these two sites, Snow Lake and Pecos in the Mesoproterozoic. So we can set up a model run where instead of turning the continental fluxes on all at once in sort of one step, and the shapes, the rates of change in here, these are fairly arbitrary. You could adjust these one way or the other. The steepness of those declines in the steady state of δ18. But if we instead turn these on in two steps, right, you sort of turn it on a little bit, you reach a steady state value of about +1 per mil, and then you turn it on sort of the rest of the way to modern values, and that causes a second decrease in the δ18 value of seawater. So we can fit our constraints relatively well with what we're calling here a two-stage continental emergence. We're turning on in this model the continental weathering fluxes in two sort of distinct steps. All right, Ben, that's great. Your model, you made your model fit your data. Good job. Are there reasons we should expect this sort of behavior, though? What can we look to in the rock record to assess the validity of this hypothesis or this suggestion? reminding ourselves too that we already do have some geologic constraints, right? So these are those same bars I showed way earlier in the talk of the estimated age of continental emergence from 3.5 billion year old angular nonconformities, passive margin deposits, thermal models. And so we can suggest then that some of these are likely indicating local emergence, but not significant emergence. And when I say significant, we can actually calculate what that means from this record. For example, to drop, depending on your assumptions of sort of what the continental crust is made of, you need something like 35 to 40% of the modern area of emerged crust to drop the seawater value from, say, +3.5 to -1 per mil. So you need at least a third to something like half of the emergent area of modern continental crust to cause this shift in oxygen isotope value in the ocean. And so these signals of emergent crust from earlier in the Archean almost certainly reflect subaerial processes, but they cannot have been, large exposed areas of continental crust, probably, isolated areas. From our data, that's what we would suggest. And so as a potential idea for a mechanism here, what I'm showing is just a histogram of detrital zircon ages, over this same time scale from 4.5 billion to today. This is just the number of ages binned into, I think I put these into 50 or 100 million year time bins. And we've all probably seen these, seen this pattern before, but I'd like to point out, right, is there's pulses, right? There's pulses in these zircon ages, and one interpretation of that is those are enhanced periods of continental crust growth, perhaps subduction, which is a really efficient way to make, continental crust. And it's worth pointing out too that the question of continental emergence is, of course, deeply intertwined with the generation of continental crust, the material, right? You can't obviously have emergence without continental crust, but they're slightly different questions, right? You can generate granitic rocks that don't get exposed subaerially. So they're super related, but they're not, it's a slightly different question. But we see these pulses, right, in detrital zircon ages, happening about 2.7 billion years ago, maybe 1.8 billion years ago. And so if we put our data and our seawater curve over this detrital zircon record, yeah, I mean, the timing of the drops in steady state values of the δ18 value of seawater coincides, at least temporally, right, with the timing of these zircon ages. So perhaps enhanced continental crust formation, maybe the onset of widespread plate tectonics around 2.8 to 3 billion years ago, generating enough crust to be emerged above sea level, can interact with the hydrosphere, weather, sequester oxygen 18, and drive this decrease in seawater δ18 value sort of in two distinct steps, perhaps related to Earth's sort of first Wilson cycles, first supercontinent cycles of crustal growth, quiescence and rifting, and coming back together. So this is our working hypothesis to explain this data. It does tend to align with some other recent work estimating growth rates of continental crust, right, the material. And so what I'm showing here is a plot from Reimnick et al. 2023. And what they did in this study is they tried to estimate the sort of the growth rate of continental crust based on whole rock geochemistry and using hafnium ages of zircons as a proxy for extraction age from the mantle. And so that's what's shown here in their plot. On this one, age goes from old on the right to young on the left, and it's volume of continental crust from 0 to 100% on the y-axis. And their work is shown in that green field there. And one of their major conclusions was they suggest basically constant continental crust growth from about the late Archean, maybe a little bit earlier, through the Mesoproterozoic. And so that timing of sort of, steady continental growth lines up pretty well with our suggested timing of seawater evolution as a response to that crustal growth, the emergence and interaction with meteoric fluids. So we're pretty consistent. Again, it's nice to not be all on your own when you're making these interpretations, right? You want to compare to these other sorts of records. And so at least with this one, we're matching up pretty well. So this is our sort of major suggestion, right, from this work is seawater was high. We resembled a water world. And the delta-18 value of seawater decreased perhaps in 2 steps over a couple steady states related to the expansion of plate tectonics, continental crust growth, and perhaps Earth's first supercontinent cycles. This is our suggestion. Of course, there's complications here, right? And so I mentioned these sedimentary records, and there's been a ton of work over many decades measuring, really carefully the delta-18 values of carbonates, of cherts, of phosphates, of iron oxides, lots of chemical sediments. And these instead show a different trend, right? They show a secular increase in their delta-18 values through time. And so I'll show some of that data here. On the right-hand side is the carbonate delta-18 values shown in per mil compared to SMO. On the left here is work showing the iron oxide oxygen isotope record. The iron oxides are really cool because their fractionation between fluid and mineral seems to be relatively insensitive to temperature. And so the suggestion is that it more reflects a change in fluid oxygen isotope composition. And there's a recent compilation by Eisen and Rousey, that came out like a couple months ago. All the chemical sedimentary records, especially Proterozoic records, show, instead of our proposed decrease in delta-18, an increase in delta-18 over time. There's a number of different explanations for this increase. It could reflect evolving ocean temperatures. Oceans could have been really hot in the deep past and have cooled through time. Perhaps it's progressive alteration, changing diagenetic environments over time, pore water evolution. Could these reflect depositional environments? I think there's a lot of really cool work that we can do next to sort of compare these records. But I wanted to be, sort of upfront, right? Our record is saying something different, perhaps, than the sedimentary records, or at least they don't obviously agree at this point. There's some other work that's done using some reactive transport models, again, based on triple oxygen isotope measurements in shales that suggest a relatively low, -12, perhaps evolving to -4 per mil seawater delta-18 in the Proterozoic. This is work from Kanzaki and Bindeman a couple years ago. There has been some work, especially focused on cherts, and I didn't show any of the chert data here, but that shows the same trend, right, as the carbonates and as the iron oxides. That suggests that maybe these cherts work on, recent cherts, and some diagenetic modeling suggests maybe something like chert could reflect diagenetic temperatures, which probably have, decreased through time. Earth has cooled through time, so you could make this prediction that the environment of early diagenesis, maybe that's also cooled through time. So I think there's some really interesting work to come out of this. What's, I think, cool though, as we try to work to reconcile both these records, I think now, especially in the Paleozoic, where we have multiple chemical sedimentary records that show a distinct seawater delta-18 trend than our altered ocean crust values. The iron oxides especially, I think, are pretty robust. So we have to think about what that means. But one of the things that I think is really cool to come out of both of these works, right? Chemical sediments from our work, is that there are ways that we can evolve seawater delta-18. And we can connect these to secular changes in tectonics, perhaps the way hydrothermal alteration works. Those are the explanations that are often used to explain an increasing delta-18 value through time. You change the balance of high to low temperature hydrothermal alteration. But I think one thing that the sedimentary records and our altered ocean crust records can say with confidence is, yeah, there are ways that seawater could change its delta-18 value. This has big implications for how we interpret, climates, weathering, continental emergence. I think there's now, a lot of timely work being done in this area that it's fun to be a part of. So I'm excited to try to work to reconcile, some of these records, maybe in a place like Pecos or other Proterozoic sites that have both hydrothermally altered crust at a VMS deposit and iron formations or iron oxide deposits in the same area, right? We can do some geographic comparisons as well. So I'm excited about that. And just in my last sort of minute here, a very shameless plug for using this inversion technique in a totally different setting. I know this is not virtual seminars in Cenozoic geology, but one thing we've been doing here is applying the same approach to settings of hydrothermal alteration by fresh water, by meteoric water. This came about because while we were testing the method initially, I was testing in all these ocean crust sites, and I was always getting about 0 per mil. I was like, oh man, am I just like adding and subtracting and I'm going to get 0 every time? I better test it in a place where I know I'm going to get a much different answer. I'm going to get a low δ18 value. So we went to these calderas in the San Juan Mountains in Colorado, which have experienced, a bunch of hydrothermal alteration over a bunch of ages. And so we can use this to reconstruct the δ18 value of meteoric water, potentially as a paleoaltimeter. We can maybe use this to investigate weathering, unroofing, and sort of connect these processes to sort of tectonic uplift, dynamic topography, these kinds of things. So I'm showing here is just results from this paper we published last year, where we're recording a decrease over time in the δ18 value of seawater at these different calderas, consistent with a rise in elevation. And again, this approach is kind of cool because we're averaging this over the lifetime of the hydrothermal cell. So we're getting sort of multi-million year averages of the δ18 value of alteration fluid, either seawater, which I talked about mostly, or meteoric water, which I'm totally shamelessly mentioning here, that we had a paper come out last year. Awesome. So just a couple sort of thoughts that I'd hope to leave you with here, after listening to me talk. And thanks again to Alex and Andre for the invitation. Really fun to participate. I've used the seminars from this series in a class. I built a whole grad class around it. And so I'm really glad to sort of give back a little bit to the community as well. I mean, the first thing here is that we can use altered crust, right, via this inverse modeling approach as a proxy for fluid or seawater δ18 values through time. I think knowing that is a really valuable first and important foundational step. Once we apply this approach to a series of hydrothermally altered crustal sites ranging in age from Cenozoic all the way back to 3.2 billion years ago, our suggestions is that there was limited continental emergence before 3 billion years ago, emerging in perhaps 2 steps related to the first supercontinent cycles, onset of widespread modern style plate tectonics. And, sort of more philosophically, taking advantage of alteration can really open up some new avenues to answer questions. And tying back to that quote I had at the beginning, water really is the cleverest substance. And so I'm very happy to take questions from everyone. And thanks for listening.
Great. Thanks, Ben. That was great. Yeah, as Ben said, we're going to switch to question time. So we have a few ways you can do that. You can click the reactions button at the bottom of your screen, and there's a raise hand button, or you can type it in the chat and I can ask it for you. Paul was active in the chat. Paul, would you like to ask yourself these questions, or should I go ahead? Okay, I'll go ahead. So Paul first asks, how thick was the 3.1 billion oceanic crust at Panorama in West Australia?
Yeah, good question, Paul. It's much less thick. It's like, let me pull up the cross section here. What is that? 2.5 to 3 kilometers here. So it's much less thick in this location than modern ocean crust. The proportion of low temperature to high temperature alteration is roughly the same. It's about 50-50 as modern crust, but yes, it is much less thick, at least in this location, than modern oceanic crust.
That's puzzling because the thickness of oceanic crust should scale with the potential temperature of the mantle. And so in the Archean, as Norm Sleep used to say, the Archean oceanic crust should be like Iceland everywhere. In other words, 20, 25 kilometers thick oceanic crust. Not so difficult.
Right. Yeah, and I don't know if maybe that's a peculiar panorama thing, right? Like maybe this is a peculiar place. I haven't yet done this approach to other settings. We went here because of the sort of exceptional preservation of that full cross section through the crust. I know there's work by Casting and others that suggest that even with a thicker crust, a higher geothermal gradient would have limited the depth of penetration of these fluids into the crust. So the water might be seeing a less thick package of rocks, even if the overall crust is thicker. That's also possible. But yeah, I think that's a good point.
And it raises
That
the
might be an
question as
answer.
to whether it's the emergence of the continents that causes the change, or a change in the volume of seawater. In the European, it may have been that the oceanic and the continental crust were not so very different in thickness.
Yeah, sure. I did those, when I was giving the estimates of how much crust had to emerge to cause that change. I did do that over, say 1 to 2 times volume, modern ocean volume, to get that sort of range. So yeah, you could produce some change in seawater given a change in ocean volume. But I think to change it, many per mil, we need some fundamental change in water rock reactions. Either it could be a hydrothermal, oceanic crust interaction, or a continental emergence interaction. But I think those are good points, and things that, with maybe a couple other sites, we could try to dig into a little bit more. But I appreciate those points.
Yeah. 2 related questions. The detrital zircon record is really a record of additions to the continental crust, and not necessarily a record of the net continental growth or continental crustal growth, because of course the zircon data doesn't tell us anything about destruction of continental crust, which is also associated with subduction. And then my third question is, you never said anything about low temperature seafloor weathering, which some people think is actually quite important.
Yeah, cool. No, good question. So a couple of things. Yes, you're right that the zircons, and this is a problem too, because I know other people have used oxygen isotopes of zircons as a proxy for continental crust growth. But the sensitivity of that proxy changes over time, because the δ18 value of continental crust, or of the source material for melting for continental crust, has probably increased over time as you build a sedimentary shell. And so the δ18 value of zircons is less sensitive to, like you say, net crustal growth or recycling over time. That's what this study from Jesse Reimnick and all tried to do. They tried to use instead whole rock geochemistry to estimate both the amount of crust production, but also the amount of crustal recycling, to get after a net crustal growth rate. And so through that analysis, we're getting the same sort of, at least consistent timing with crustal growth. So yeah, I appreciate both those points. This approach with crustal recycling estimates is at least consistent with our timing for changes in seawater δ18. And you're saying, oh, low temperature seafloor weathering. Yeah. So our approach here, we're gonna integrate whatever water rock reactions happened over the lifetime of that crust, right? While I was seeing that, the majority of fluids, especially through the high temperature section, happen, relatively quickly over the first several million years. But as long as we preserve that uppermost section of crust where seafloor weathering might have been important, we're gonna account for that in this inversion approach. I didn't show it. I don't have any good figures pulled up, but one thing that pops out of this is we get fluid flow vectors, right? So we can sort of estimate the time integrated average fluid amount, fluid flow directions through these places. And yeah, you do see, changes in that. So the approach here should be able to handle any, seafloor weathering that occurs at these sites over time. That should be reflected in our sort of inverted estimates for initial fluid δ18 values. Yeah.
Sorry, I was spaced out for a second myself. Sorry. Every now and then. Okay, Greg, you had your hand up next.
Yeah, that was inspiring, Ben. Now I have one short question, which is just a clarification, and then another more provocative one, perhaps. My reading of your inverse modeling is that the Muhlenbach's idea that seafloor spreading controls oxygen isotopic composition of the ocean is out the window, right? It failed.
Oh, no, I think, no, that still holds. I think that's by far the biggest lever that controls the δ18 value of seawater.
So you're not arguing that the continents are controlling it then?
They both do. Continents are one of the top two that control the seawater value, but no, the hydrothermal circulation of seafloor is super important. I mean, that's what causes this initial drop, say from 6 per mil down to whatever it settles at, depending on continental fluxes. Yeah, no. So that original Muhlenbach
Well,
thing is totally
yeah, that's an interesting drop because it's based partly on theory, but the other one, the dotted line or the dot dash line, that one, isn't that a failure of the Muhlenbach model?
No, because that model, well, I mean, the idea that seafloor alteration buffers oceanic δ18, I think that holds. And the model here I'm showing is calibrated towards modern values, all the modern fluxes. And so it reproduces modern values totally fine. And it does Phanerozoic values fine. It does, neoproterozoic values fine. But and in that version with the steep drop all the way to modern, I have the continental weathering on as well, just as a demonstration. So I think the idea is totally solid, but there's also continental weathering that can affect it as well. It's both together, I think, that buffer this value over multi-million year timescales.
Thanks for that.
Muhlenbach argued that the δ18 of seawater couldn't change. And so the lower curve is actually completely consistent with Muhlenbach's.
Right. Well, my more provocative question then is, what about the whole effect being due to change of life on land? The change from actinobacterial, cyanobacterial communities to eukaryotic weathering on land?
Sure. I mean, our results, and I think this is, consistent with some of the geologic record too. You first see the first like widespread passive margin deposits at like 2.7 billion years ago. And so, I mean, I know there are certainly examples of subaerial settings in the Archean. There's just not enough available material to weather to affect the ocean's δ18 value. I think it's a mass balance problem at that point. So I think you really do you're sort of limited by substrate until a lot of continental area comes up. And then I think it's more related to like mineralogy of the continents, the development of clays and a sedimentary shell on top of granite. Those have a pretty high δ18 value compared to, say, granite where it started. So, I mean, I think that, a change in weathering driven by some biologic evolution could affect the rate at which it drops, but I don't know if it could affect the magnitude of the drop or control that part of it. I could see how it could influence how quickly it drops. If you're weathering more quickly because of biotic changes, sure, that could change the steepness of these curves. But I think to get from 3 per mil down to -1, you really do need lots of continental crustal material available to be weathered and sequester δ18. That would be my thought.
Yeah, but if life were more efficient at weathering, and particularly Rubisco fractionations were more efficient between the isotopologues of the CO2, then even small areas of land in the Archean would have a more profound effect than if there were no life there.
Yeah, but you'd still need, delivery of new continental crustal material in order for it to be weathered. I think you could be substrate limited, is what I would say.
We do actually have evidence of life on land going way back from phosphorus depletions and microfossils and all sorts of stuff.
Yeah,
I'll
sure.
send you some papers, but it's very thought-provoking. Thanks again.
Yeah, thanks. Thanks for the questions.
Most weathering occurs in mountains, which are not heavily vegetated.
Oh, I don't believe that, Paul. I'm sorry, but there's a lot of evidence against that view. The higher you go, the less the weathering because it's too cold and often covered in snow.
The lowlands develop mature weathering profiles, and so you're not introducing any new unweathered continental crust.
The recent work on the flux of carbon on the planet shows that the weathering and the carbon cycle is most active on the plains. But that's a whole other debate.
Let's go ahead and move on to the next question here. But it's always
Thanks
fun to
again.
see those interactions. Cool. So Karthik Sendersar1 in the chat asked, how do you deal with singular QI matrices if any QI matrices have a zero determinant, i.e., how do you maintain the consistency of the square matrices?
Maintain the consistency. Oh, it's a method, sort of a question about the matrix. Well, I think I understand the question. We're performing a sort of a least squares inversion approach here, and I don't actually show the full like matrix inversion equation here, but we're using this approach that was developed by Wunsch in 1996 for oceanographic work, and you need to involve an identity matrix, and we have a smoothing parameter in there that's tuned based on some other sort of model inversion results. So the full approach here is not quite shown. If you're interested, I can definitely send you the paper with the more detailed methodology, but I'm not actually showing the actual matrix inversion equation here. That's a little more nuanced, and so I didn't toss that in. But it is basically the same setup that's used in tracer mass balance work in oceanographic literature. So this has been sort of developed over the past like 40 years, the basis for this work, mathematical basis anyway. Yeah, thanks.
All right. Cool. So I don't see anything. Andre, did you have a question?
Yeah, good talk, Ben. I have two questions, maybe ask separately. So the first one about two-stage, it's kind of like we're always limited by amount of data we have. So maybe if you would get more data, it would call like for 3-stage or more stages. But anyway, did you try to play with this curve of sort of gradual change through time that, I mean, would it address your trend anyway? Like, why do you need 2-stage?
Yeah, totally. No, I think you're right. You could equally fit this data with, sort of I think you still need this initial drop, right, from this high value to some steady state value that's +3, +4 per mil. But then this decrease, yeah, you could fit it with almost a, I guess, not exponential, but yeah, like a decrease, a smoother decrease, I think could intersect that data equally well. I think that might align more with this sort of approach where they suggested consistent continental crust generation over this time window. Yeah, so I think you could totally fit the data that way as well. We, thought this 2-stage idea maybe would align with some geologic evidence for, crustal growth, rifting, quiescence, and coming back together. But yeah, you could definitely fit it with a gradual change as well. We had a paper in 2020 that just had the panorama point, this 3.24 billion-year-old point, and yeah, we had a scenario in there of gradual change towards modern in there, and I sort of forget what the rate values are from that paper, so I can't give you like a number off the top of my head, but yeah, you could fit this with a gradual change as well. And so I think you're right, filling this in with a couple more places, and there are places, right? There are these sites across these ages. That's what makes it kind of cool, is we can add to the sedimentary picture with this approach.
And the second question, so you see positive values going down, and you explain it with emergence of continents, but I guess another control would be a hydrothermal alteration. And we know if sea level, if continents didn't exist, probably water depth was different and mantle temperature is different. So maybe thermal gradient was different through oceanic crust. So the transition from high temperature to low temperature weathering or alteration in the oceanic crust was a different depth. Did you think like how pressure and temperature could have changed sort of high temperature, low temperature alteration in oceanic crust?
Yeah, for sure. No, that's a good point. You're right that another way to explain this is that hydrothermal alteration of oceanic crust was dominated by high temperature interactions in the Archean that gradually evolved towards what today has a greater proportion of low temperature alteration. It's interesting because some of the earlier sort of work, I'm calling back to Casting and others, suggest in fact the opposite is that they were trying to explain this observed increase in the δ18 value of chemical sediments, perhaps by an increasing seawater δ18 value. And the thought there was that a higher geothermal gradient would limit the sort of depth to which fluids could descend in the crust, because the crust was more ductile. You don't get fractures and cracks as easily to as great of depths in the crust. So you're actually more dominated by shallow and low temperature alteration in the Archean. And then as the mantle and crust cooled, that allowed for deeper penetration of hydrothermal fluids before they reach that sort of temperature of 350 to 400 degrees C, where I'd want to come back up to the surface. Yeah, I mean, I think that's a testable hypothesis. The temperatures of yeah, it's interesting. The temperatures of alteration at Panorama are based on fluid inclusion data, and they're very similar to what we see at modern, hydrothermal settings. But if you, went to other sites, did some geothermometry, and I don't know this offhand, you could, try to calculate the average temperature of hydrothermal alteration and see how that influences it. Yeah, I mean, you can sort of reproduce this curve if you're changing the balance of high to low temperature alteration without changing the continents or keeping continental emergence at 0. But at least the evidence from a site like Panorama and some other Archean hydrothermal sites suggests there was not a big change, at least in the proportion of high to low temperature alteration based on mineralogy, oxygen isotopes, geothermometry. So you're right, you can change it, but at least now the evidence is that it hasn't changed a ton over Earth history.
Thank you.
All right, thanks, Andre. We have one from Daniel Brandy Mills. Please go ahead and unmute yourself. You're still muted, Daniel.
There you go. Can you hear me? All right, great. Hey, Ben.
Hey.
In light of all this, could you just explicitly respond and help me understand claims that Archean sea surface temperatures were like above 70 degrees C or so? Like, how does this all fit into that, and what's your response to those interpretations?
Yeah, sure. So that, one of the ways you could explain, the sort of these trends, not the iron oxides, they don't go back far enough. Yeah, is that the oceans were really hot. If you take our values for cash, and assume that the carbonate values or the chert values, for example, record primary seawater, it makes the ocean even hotter, right? It doesn't help that way. However, I think, there's growing body of work, especially looking at, I mentioned that these triple oxygen isotopes in cherts and in barytes, those suggest that they reflect some higher temperature fluid and not primary seawater composition. So I think, there's still pieces of evidence on both sides, but I think there's a growing body of work that suggests that these cherts, probably the carbonates, for sure, may represent or record non-ambient seawater conditions, whether that's hydrothermal or diagenetic, I don't know. But there's moving evidence towards those values not reflecting super hot Archean oceans, is what I would say.
All right, yeah, thank you.
Yeah, thanks.
Okay, and maybe I can ask something that's a little more on the basic side, and maybe I just kind of missed along the way, but do these hydrothermal interactions have any dependence on composition, like felsic versus mafic?
The direction, that's a good question. Yes, it depends, 2 points. One is that, this relationship holds regardless of rock type, right? Low temperatures, you tend to enrich the rock. What happens though does depend a little bit on the composition of the net change you see does depend on the composition of the starting fluid and on the starting composition of the rock. You'll get a different pattern if you're altering a granite with meteoric water than a basalt with oceanic water. So that's one of the things we really do have to constrain for this inversion technique is the starting δ18 value of the rock. We have to get a really good handle on that, because if you move it up or down, you know, a couple per mil, that has a couple per mil influence on the calculated inversion. So yeah, there is a dependence on lithology. The same approach is still valid here, but you do have to adjust some of the inputs. Some of the fractionation factors are a little different, you know, for basalt or granite. But the same approach is still valid. But you do really have to have a tight handle on the starting δ18 value of the setting, which you can get either from tectonic setting or from an unaltered sample that's nearby, right? Those are the two ways we try to go about that.
Okay. Yeah, I find it interesting because what you're going to lose when you have emergence isn't your interaction with mafic oceanic crust, but with felsic continental crust. Because if you're still differentiating and creating continental crust early on, even if it's still submerged. So, and that I think brings me to a broader question that kind of a lot of the discussion here is suggested or hinted at is like, so you're doing this from a 2D perspective, but could you picture more of a 3D perspective, that a model that, you know, incorporates this depth aspect to it? And how do you think it's realistic, and how do you think it would look, or would it change this?
Yeah, no, good question. I mean, I have thought about that. I mean, in reality, this is like a super skinny 3D reconstruction. So we take these, you know, these values from these rocks that are, you know, of course, found in 3D and project them onto a one centimeter thick slice. That's our 2D reconstruction. You know, I think that as long as we're capturing the full picture of a hydrothermal cell, you know, we're getting at least some of the low temperature stuff, at least some of the really high temperature stuff. My intuition is that this sort of interpolation and regridding process should be pretty good at getting after it. Yeah, it would be awesome to verify that by adding a third dimension. It might be a challenge to find appropriate outcrops where you could do that. One of the other things you need to have a good handle on here is the geometry of the outcrops, right? And it's because we're doing mass balance, so you need to have a pretty tight handle on the volume of rock that's one of the fundamental things that goes into this equation, this R value here. We need to know the volume of rock. Yeah, so I think it would be nice to validate it. I don't know of a site offhand, right, where we could do that exactly, but yeah, I think that would be a really good test to see, okay, what if we're actually capturing, because this process is happening in 3 dimensions. You could just add more equations, you add more boxes, you make these cubes instead of boxes. I think mathematically, I don't think it's a huge step up in complexity, but you'd want to be really careful of selecting the site or sites to test that on, would be my thought on that. Yeah, it's a good point though. I think that'd be awesome to do.
Cool. All right, thanks. I'll leave a few seconds in case anybody else wants to speak up and ask a question. Okay, Greg, go ahead. Go ahead, please.
Yeah, just following on from Alex's question, which is really interesting. Your panorama site is a rather thin, as Paul pointed out, sequence of basalt on granite. Is that really an analog for deep ocean crust?
No, but 2 things to say that. Yeah, totally right. 2 things to say to that. There's lots of good evidence from the mineralogy, from fluid inclusions, that the granite did not participate in the hydrothermal circulation. It was limited to the volcanic pile. And so, yeah, it's definitely not a perfect tectonic or geologic analogy to modern oceanic crust. But the important thing here is there's pillow basalts, there's exhalite cherts over the area. It's pretty clearly a marine environment. Yeah, the heat source is different than we get in like modern mid-ocean ridges, but they do seem to have been isolated during hydrothermal alteration. The volcanic pile and is isolated from that Strelly granite hydrothermally.
Very good, thanks.
Yeah, thanks.
All right, Cool. Well, we've held you for 20 past the hour, Ben, so this was really good. Really cool to see your work. And thanks a bunch again for stepping in last minute.
Yeah, no, appreciate it. Thank you guys.
All right, everybody, take
Good to see
care,
you, Ben.
and
Thank
Good to see you.
we'll see you all next week.
All right. Thanks, everyone.